Let's talk about the graphs of log functions. So we started with y is equal to 2 to the x, which is an exponential function. It looks like the following. 2 is bigger than 1, so it's increasing from left to right. It goes to the point 0, 1. Its domain is negative infinity off to infinity, and its range is 0 off to infinity. We had mentioned that logs are the inverses of exponentials. So to find the inverse, you interchange your variables. So the inverse is x is equal to 2 to the y. And then you're supposed to solve for y, which is really hard to do until logs were invented. So x is equal to 2 to the y means exactly the same thing as y is equal to a log base 2 of x. In other words, a log base 2 of x is the power that you raise 2 to get x. Okay, so it's a little easier to work with x is equal to 2 to the y, and so I've built my table just like I did before, except I'm choosing my y values this time. So I'm choosing y is equal to 3, 2, 1, 0, negative 1, negative 2, negative 3, and I'm plugging that in for y. That means x is equal to 2 to the third, which is 8, so 8, 3 should be a point on that graph. Continuing on down through, here are the points we get, and I graph them over here, and you can see that this inverse, or this log, is a reflection of that exponential across the line y is equal to x, which is what we were expecting. That's how inverses work. I now have the point 1, 0 instead of 0, 1 because they're interchanging. And you can see my domain and my range are swapped. The domain of a log is only open 0 off to infinity. It only exists to the right of the y-axis. Yet its range is everything. It goes all the way up and all the way down. It's really slowly going up, but it will continue to go up for forever. You can see it's screaming down fast in general. So the thing we want to add to our toolkit functions is a y is equal to log base b of x, where b is bigger than 1. We'll just focus on b is bigger than 1 in this class. That's plenty to think about. So in general, my graphs are going to start like this. It's going to go through the point 1, 0. Its domain is going to be 0 off to infinity. Its range is going to be negative infinity off to infinity. It's everything. And this time it has a vertical asymptote of x is equal to 0. It'll never hit the y-axis, which is x is equal to 0. Okay? So that thought in mind, let's draw a couple graphs. Let's go with f of x is equal to log of x minus 2. Now you don't see a base explicitly written, so that means my base is base 10. 10 is bigger than 1, so give or take, I'm starting with this guy. So here is y is equal to log of x, and it goes through the point 1, 0. Now that minus 2 is inside the function, so it's going to move it to the right by 2. So my vertical asymptote was at x is equal to 0. If I move it to the right by 2, that's now at x is equal to 2. And if I move that point 1, 0, 2 to the right, I'm now sitting at 3, 0. So here is my graph, give or take, of log of x minus 2. So you can see my domain is open 2 off to infinity. My range is still everything. Goes all the way up, all the way down. And my vertical asymptote, VA, short for that, is going to be x is equal to 2. Next one, natural log of x minus 4. Natural log of x is a base e. E is about 2.7 something, something, something. That's bigger than 1, so it's going to start like this. Here's the natural log of x. And that minus 4, well, that's outside the function, so I'm going to shift it down by 4. So my vertical asymptote is staying right where it's at because I'm not moving left or right. I'm only going down by 4, so 1, 2, 3, 4 down. There should now be 1, negative 4 is that point that I was interested in. And it's still a vertical asymptote. If I extend this, y is equal to 0. Excuse me, x is equal to 0. X is equal to 0. Extend the y-axis. That's x is equal to 0. And I get that guy. So this is the natural log of x minus 4. So my domain, it still only exists to the right of x is equal to 0. So 0 off to infinity. Its range is still all real numbers. Goes all the way up, goes all the way down. And its vertical asymptote is still x is equal to 0. Alright, next one. Let's talk about log base 3 of x plus 1 plus 4. A couple things going on, but I'm going to start with a log base 3 of x. 3 is bigger than 1, so it's going to look like the following roughly. It goes through the point 1, 0. Alright, these are both additions, so I can choose which one to do first. I'll do the plus 1 first for no good reason. Plus 1 is inside the function, so I'm affecting the x's. It's going to go left by 1. Right now my vertical asymptote is at x is equal to 0, so if I move that to the left by 1, I'm sitting over at x is equal to negative 1. If I move this point over by 1, I'm now sitting at 0, 0. Woo! swear it looks like the other one. This is log base 3 of x plus 1. Okay? Now that plus 4 is outside the function, so that's affecting y, so it's going to go up by 4. So this point 0, 0 is now up at 0, comma 4. I didn't move left or right, so that vertical asymptote is still the same. So it's coming sneaking through here like that. So there is y is equal to a log base 3 of x plus 1 plus 4. Its domain, you can see I can go almost to -1, not quite, so -1 off to infinity. Range, I'm going to hit everything up and down. And my vertical asymptote is at x is equal to -1 now. This leads to talking about, well, the domains of logs in general. Well, you can't take a log of 0 or a negative number. You can see that on the original toolkit function. It only exists to the right of x is equal to 0. So whatever you plug into a log has to be positive. So if I'm looking for the domain of f of x is equal to log base 4 of x minus 6, what I have inside the log better be positive or I have a problem. So I need x minus 6 to be greater than 0. And if you solve that, that means x is greater than 6. So the domain of this is x is greater than 6, which is an open 6 off to infinity if you write it in interval form. On this other one, g of x is equal to a log of x squared plus 2x minus 8. Well, that means x squared plus 2x minus 8 better be positive. Well, we're better at figuring out when it's 0. So let's see. I think that one factors, doesn't it? X plus 4, x minus 2. So that's equal to 0 at x is equal to -4 and 2. That's a problem. Well, if you think about the number line or just the graph of x squared plus 2x minus 8, here's -4, 0. Here's 2, 0. This one opens up because it's a positive x squared, so give or take, that looks a little like this. Well, I want when it's positive, so I want over here and over here. So the domain of this is going to be -infinity to -4 union 2 off to infinity. You could see that if you use the number line instead, so just to add in that thought, here's -4, there's 2. Pick a number over here like, say, -10. If you plug in -10, x plus 4 will be negative, and x minus 2 will also be negative, so I'll have a negative times a negative. That's positive. If I pick x equals 0 in the middle, I'm going to get a positive times a negative. That's negative. And over here, if you pick like x is equal to 10, you'll get a positive times a positive. That's positive, so I want these outer ones, these two, which still gets me to -infinity to -4 union 2 off to infinity for the domain of g of x is equal to a log of x squared plus 2x minus 8, because again, I need a log of a positive number. You can't take a log of 0 or a negative number.